All right, so we're going to take a look at example one to kind of give you a little bit of an idea of what calculus is and the difference between your pre-calculus skills and how we apply a limiting process to turn it into a calculus problem. So what we're going to do is we're going to take a look at this circle right here, this disk. And what I really want to do is I want to find the area of this disk. That's my target, my task. Excuse me. So what we want to do is we want to say, what do we know? What are we given? What pre-calculus things are we going to know to use? So suppose we know that the equation for the circumference is 2 pi r. So that is going to be our given. We know how to calculate circumference. Let's add to this. And let's say we also know how to find the area of a rectangle, which is going to be your base times your height. And we're going to know how to find the area of a triangle, 1/2 times base times height. So we're going to say that these are the things that we know how to do. And we're trying to find the area of a circle. And yes, I know we know what the formula is, but let's assume we had no idea what that area formula is. We just want to find the area of this non-standard shape, given the skill set that we have that came before. How do I find circumference? How do I find the area of a rectangle? How do I find the area of a triangle? So part of what calculus does is it says, okay, if I don't know how to calculate this directly, how can I get there by estimating it? We kind of start with this gray area and say, let's break it up into smaller pieces. So we're going to choose in this case to take our disk and we're going to cut it up into these little donut shapes, these little concentric circles. And each concentric circle is going to have a radius that gets larger and larger. So this would be your center point. You will have a nice little center point there that kind of has no radius. And then you move out with each of these little consecutive rings. And hopefully you would agree that at this point, just me cutting this shape into these consecutive concentric rings, that the area of the original circle is going to equal the sum of the area of each of the rings, the sum of the area of the rings. So they're still the same. Now you're like, well, why might I do that? If I cut them into these little concentric circles, then what I want to do is say, let's take one ring and let's just take a look at it. Remember, what we're trying to do is to turn it into a problem we already know how to do, into a pre-calculus problem. How do I calculate area? And what I know is circumference, area of a triangle, area of a rectangle. So I decide at this point that what I'm going to do is I'm going to take my concentric donut, one of them, and I'm going to slice it right there. And when I do that slice, I'm going to take it and I'm going to open it up and bend it out so that it turns into a long, skinny shape. And you know, your gut feeling says, hey, I'm going to turn it into a rectangle. But now let's think about this turning it into a rectangle. That when you're looking at this, is it truly a rectangular shape? Remember, I'm not really trying to morph it. It's not Play-Doh that's going to change the shape. I'm just taking it and kind of straightening it out like that. And if you think about it, it's not quite a rectangle. If you look at your radius from the center to the inner, that circumference of the inner ring is going to be a little bit smaller than the circumference all the way to the outer ring because there are two different radii that you're looking at. So technically, when we take a look at this, the inner portion will make that the top is a little bit shorter than the bottom portion. So it doesn't really make a rectangle. It's a kind of a trapezoid shape. But for our intents and purposes, we kind of go, oh, it's close enough to a rectangle that what we can do is ignore the fact that one side's shorter than the other. We'll just go ahead, let's go with the larger one, fill in this little section and look at it as a rectangle. Now what that means is that this area is now an overestimate of the area of the original disk. But that's okay. We cut it up and we put it into smaller calculable things, and it's okay if it's a little off, a little gray area. We don't really care about that. We're going to fix that shortly. And so when we do that, now we can calculate the area of the rectangle, because we're going to the larger side, the width, or the length right here is going to be 2 pi r, and we'll call this part right here delta r. That's going to be the set width of each of the rings that we're going to be looking at. And maybe we choose to be 1 centimeter, maybe we choose a millimeter, maybe we choose an inch. You know, that's given the problem how we're going to cut it up. And so we're going to repeat that, and we're going to take each of these rings, starting with the little point that of course has no area, cut them up, straighten them out, and then line them up, starting here at the origin for the one that has no height and moving along. So we'll go out 1 inch to get to the first one. We'll go out 2 inches, we'll go out 3 inches, or centimeters, or whatever units we are, dot, 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 until we get to the maximum radius, which was of the disk. And so we look at this little figure and we say, what do we know? Is this exactly the same area as the original? No, because each of these is a little bit too big because we're going to the outer edge, but that's perfectly fine. And then we say, okay, how can I get a better estimate? What am I going to do to create something that adds a limiting process to it? So I started thinking to myself, well, if I have each disk a width of 1 inch, and then maybe I change it to a width of 1 centimeter. Notice that when I do that, if I have a much skinnier width, that means that the difference in the radii lengths are not as much. So the difference in the circumference from the bottom piece and the top piece would be closer. So it might still be an overestimate, but it's less of an overestimate than it was. And so maybe instead of doing 1 centimeter, maybe I decide to do 1 millimeter. And every time I make the width of the ring a little bit shorter, what I'm doing is putting this limiting process, and we're going to do the limit. We're going to let the number of rectangles go to infinity. Or another way of looking at this is to say we're going to let the change in r go to 0, because as delta r goes to 0, the width of each ring, I'll have more rectangles and it'll be a better estimate. So the idea here is that with this limiting process, even though technically we're not going to be too tedious to calculate it, but what we would do is eventually each of these rectangles would be so skinny that there would not be any more of the jaggedness that we're seeing right here. And this set of rectangles, as the n goes to infinity, the number of rectangles, we're going to turn that rectangle into a triangle of which we know how to calculate the area of. So again, we went kind of from exact, cut it up into little pieces. Then we transformed it a little bit. We were a little off. There's a little gray area, but we could calculate it very easy. We apply this limiting process, which then helps us kind of eliminate the error in our measurements that we had. The fudge factor starts to go away, becomes more and more of a better estimate as we do that. And so eventually, as n goes to infinity, when we do this limiting process, we turn it back into an exact problem. This area is exactly the same as the area of that original disk that we were looking at. And how do you find the area of a triangle? 1/2 your base, which is the radius, because you go, how far out did I go this way, to the maximum radius of the actual disk, times the circumference of the actual circumference of the disk going all the way around. And so, and notice very nicely, as expected, this formula is pi r squared. So our key idea is we took a disk, we split it into smaller and smaller parts of things that we could calculate using prior skills in pre-calculus, area of a rectangle, area of a triangle, and so on. And then we put it back together in a slightly different way, and it's okay if it's really an estimate, because we fix the estimate with the limiting process, which then allows us to find the answer that we could not calculate directly. So we kind of went from exact, fudging it a little bit, and then back into exact. And so that's the kind of the pattern that we're going to follow with a lot of our calculus problems that we're looking at. Big things are made of little things are easier to work with, and then the limiting process helps us find the answers we could not calculate directly. All right, that'll stop our intro to calculus. This is part 2, showing you the example of calculus, the limiting process, and how that works.